Hello students, welcome to Inside Physics. Today we are going to discuss about the hysteresis process, hysteresis loop. It is a graph represents the magnetization and demagnetization of ferromagnetic materials when they are externally applied with a magnetic field. So, history of a magnetic material is very useful in understanding the magnetization and demagnetization of a ferromagnetic material. Why we take a ferromagnetic material means it is more susceptible compared to para and dia. A ferromagnetic material gives instantaneous process of demagnetization or magnetization, and the process is very instant when we apply an external magnetic field. So here, what is the importance of hysteresis loop? It actually briefs the some properties, magnetic properties of a particular ferromagnetic material. We know that the susceptibility of a ferromagnetic material is far greater than 1. So here I will explain the hysteresis curve or loop where we can understand by this diagram the H. H means applied magnetic field. B, magnetic flux density. So we are taking a graph which is represents the whole process cycle of magnetization and demagnetization, and it happens only when the material is in an external strong magnetic field. So if you understand this, it is the origin where we take the initial magnetization. First of all, we assume that the ferromagnetic material is having zero net magnetic moment. That means we can consider it as a virgin magnetic material with a net zero magnetic moment. That means all the magnetic moments will be cancelling each other because of their random orientation due to thermal condition of the material. So here initial magnetization is represented by these dotted lines with OA. Okay, that means you observe whenever we are applying the magnetic field and we are increasing in the way the magnetic induction or flux density inside the material will also increase. So continuously increasing as per this dotted line, and at this particular juncture the applied magnetic field, even though it is increased, the magnetization, rather the flux density inside the material, it has come to a saturation point. Okay, so saturation point is where all the dipoles, magnetic dipoles inside a ferromagnetic material are all oriented according to the magnetic field, in the direction of the magnetic field, and the orientation, the magnetization is complete, then it reaches a saturation limit. So the flux density or magnetic induction causes the magnetization. Magnetization is because of the result of magnetic flux density present inside the material caused by the applied external magnetic field. So here if you observe this graph, we have reached a limit here where the further increase of the magnetic field is not increasing any flux density, and thereby it is not causing any more magnetization. So here, from here we are coming like this backwards. That means the magnetic field slowly is decreasing. So see here, the magnetic field is getting decreased, and even though the applied magnetic field has come to zero, but the inside flux density remained to this extent. This is the magnetic flux density, that is magnetization, remained inside the material even though the applied external magnetic field has brought to zero. That means this is a limit called BR. That means magnetic induction of retentive magnetic induction, retained magnetization. We call it as retained magnetization, and it is the positive side of applied magnetic field. And we are coming to the negative side. Whenever the applied magnetic field has brought to zero, there is a residual magnetization, and this magnetic induction is not becoming zero. That is the important point. That means the metal has retained some magnetization. Why? External magnetic field has brought to zero. Why is this magnetization is still present inside the ferromagnetic material? Means that is the basic property of a ferromagnetic material. It actually responds to the external magnetic field very quickly, and even though the applied field brought to zero, but the magnetization does not come to zero. That is a useful property. So retained magnetization can make a material into a good magnet, a permanent magnet. It may be a soft magnet or hard magnet dependent on its nature of the material. So here, see, the applied magnetic field has been reversed from here to here. That means the negative side of applied magnetic field means compared to the beginning, we have reversed the direction of magnetic field. Then what happened? Again, see, this residual magnetization remained in this material as slowly coming down, and the magnetization has come to zero at a point called HC. That means magnetic field, coercive magnetic field, coercivity. What is meant by coercivity? And here I used a word, retentive magnetization or remanence magnetization. So retentivity and coercivity, these are the two terms which we need to understand when we are studying the hysteresis loop. This hysteresis is mainly represents the history of the magnetization. So when we brought the magnetic field to zero, this is the history of this material. That means even though we have come to zero as far as magnetic field is concerned, there is a magnetization present and it is not becoming zero. That becomes the history to the next step. That's what hysteresis is all about. Here, see, this is the coercive magnetic field. Coercivity means that is the amount of magnetic field that must be applied in the reverse direction to bring the magnetic induction flux density or magnetization to zero. So we need to apply the magnetic field in the reverse direction so that the residual magnetization has brought to zero. So what is retentive? Retentive magnetization or remanence, retentivity or remanence. It is the residual magnetization that has in the material even though the external magnetic field has brought to zero. So these two terms you must remember. And again, here we are coming to the negative side of magnetic induction. It is the positive side, it is the negative side. And again, if you observe, the reverse directed magnetic field has been increased. So even though the reverse in the direction of first two, in this positive direction, and next in the negative direction, we are increasing the magnetic field again. Then what happened? See, at a particular point here, at this point, the magnetic induction is also being increased in the negative side, opposite to this side. So it has come to a saturation point again. Here is the saturation, and you can observe that the magnetic induction has become a straight line. So that means even though the magnetic field in the reverse direction is increased, the magnetization has come to a saturation point. It cannot be increased further. So we will move towards this line again. So here we are decreasing the reverse magnetic field and has brought to zero. Then even then there is a residual magnetization. This is this from here to here, residual magnetization, that means retentive induction or retentive magnetization, and the property of this kind of property of a material is called retentivity of that particular material. Again you see, from here the magnetic field is increased and we have come to the positive side of the magnetic field. That means we have reversed the direction to increase the magnetic induction again. So this residual magnetization after reversing the magnetic field has come to zero here. That means what we are doing is, this is a loop representing the magnetization and demagnetization. If you want to demagnetize a material and you must bring the magnetic induction inside the material to zero, means you must be applying a coercive force. What is that coercive force? The magnetic field in the reverse direction. If you apply the magnetic field in the positive direction, magnetic induction has increased, and even though it has brought to zero, this has not come to zero. That means if you want to bring down this magnetization to zero, you need to apply the magnetic field in reverse direction. So this is the loop represents magnetization and demagnetization, and this entire area of this loop, the area inside this loop presents the loss, what is called that magnetic loss, hysteresis loss we may call it, hysteresis loss. The energy spent to bring these domains inside a ferromagnetic material into the magnetic field orientation, the energy spent to orient all the domains, we will see what does the domains, how does the domains related to this hysteresis process also. Now, okay, here we will complete this graph procedure, and here again the magnetic field is increased, again the induction is coming to the next levels, so that step by step it is also increased. You can see the two arrows here, this one and this one. So once the graph is starting from here to here, we will use this arrow, and again if you are coming back by decreasing the magnetic field, we will use the arrow into the backward direction. So this is about the hysteresis loop, and now we see how this hysteresis process can be explained on the basis of ferromagnetic domains. Ferromagnetic domains. We have seen this domain theory in my previous video. So what is a domain? It is a space, or it is a boundary, or it is an area. What it is? What is a domain? Ferromagnetic domain. It is a space assumed to understand the magnetic behavior of the ferromagnetic material, so that we can actually expand this kind of nature throughout the material by considering small domains which are nothing but the small space assumed by us across over the whole material. So this is the domain. Now how to represent the domain orientation? How do they actually orient? There are two types. Okay. So domain wall movement. Domain wall movement. So the magnetization happens generally in two ways. Okay. or we may call it as motion of domain walls also. And the second one, rotation of rotation or orientation, we may call rotation of domains. So these are the two processes on which we can explain the hysteresis behavior. So in the weak fields, domain wall movement, we may consider a material and we can have n number of domains inside the material. Okay, so inside this domain we can have the atoms or molecules which are actually behaving as a magnetic dipoles, so that they will be orienting inside the magnetic material, magnetic field applied. So if the magnetic moment vector present inside the domain or space is oriented in all directions before applying an external magnetic field. So the domain wall movement actually happens in a weak field. So here weak field actually tries to expand the domain walls, or we may call it as the motion of domain walls. So these walls will gradually orient all the magnetic dipoles, which are nothing but atoms or molecules or ions present in the material. So all the magnetic moment vectors will be oriented in the direction of the magnetic field. So the orientation happens generally, see, if you consider an atom as a dipole which is having an intrinsic dipole moment. So the dipoles are considered as polar and non-polar. Here when you are considering the magnetic dipole, it must contain a north pole and a south pole. So that is the orientation in which the magnetic dipole is oriented along the direction of the magnetic field. So that means here we can just picturize what is going on inside a ferromagnetic material. This is what happens after the complete magnetization. So this motion of the boundary of these walls will be expanding at the cost of diminishing unfavorable domains. We may call some favorable and unfavorable domains in this context. Favorable means which are orienting in the direction of the applied field very quickly. They are favorable. And unfavorable means they may not be responding that much quickly. So the favorable domains expands their walls, they move very quickly, and all the material, all the domains will be coming into a single domain by expanding the walls of the domains at the expense of unfavorable domains. So this is what the motion of or domain wall movement actually behaves inside a ferromagnetic material. So next one, rotation of domains, rotation or orientation. So how this will happen? This will be happening in a strong magnetic field. Strong magnetic field. When a strong magnetic field is applied, what happens? The process of magnetization is very instantaneous, and the each domain what we have picturized just now, the orientation of all the domains will be very instantaneous, and the magnetization percentage also increases. That means the net magnetic dipole moment is also increased considerably. So is there any, this is the two processes where the domain wall movement or the orientation of domains occurs based on the field strength we have applied. This happens in a weak field, already I told you. Okay, so is there any hindrance to these kind of domain wall movement or orientations? Yes, the thermal condition, the temperature of the material sometimes obstructs the rotation or domain wall movement. So the thermal agitation of the atoms or molecule inside the material disturbs the smooth process of the domain orientation. That is the one of the reason. And the second one, if there are any impurities present inside the ferromagnetic material, the impurities do not actually orient. The impurity atoms or dipoles actually do not contribute any magnetic moment to the overall net magnetic moment of the material. So, and other thing, the dislocations. Dislocations means inside the material, if there is any cracks or if there is any dislocations happening, then net magnetization may be not up to the mark what we have expected. And the next one, what we actually feel like a hindrance is that magnetization is also affected. The net magnetization is also affected because of the non-magnetic inclusions present inside the material. Non-magnetic inclusions, that means sometimes some other materials may be present as impurities. Okay, impurities are two types. The doping we do, sometimes some materials are required to dope to change their magnetic and electrical properties. Sometimes there may be a natural tendency of some materials which may have the impurities. They are called non-magnetic inclusions inside the material. So we have seen three hindrances for the smooth process of magnetization and demagnetization. So overall, this process is useful to understand some beautiful properties of a magnetic material, and what are those magnetic properties that we can understand with the help of this hysteresis loop. For first one, we already seen that is retentivity, already discussed. Second one, coercivity, that is also discussed. Third one, permeability. Permeability is nothing but the tendency of the magnetic material to accept the magnetic lines of force to pass through it. So permission to be given to the magnetic lines to pass through the given material. So permeability of a free space is always represented by mu naught in the magnetic processes. And third one, these are all the magnetic properties of these materials which are very useful in understanding the material. And the fourth one, reluctance. Reluctance is the tendency of not responding to the applied magnetic field. So it is reluctant. So I will not come into the orientation even though when you apply very strong magnetic field. That's what it says. It is very reluctance. So it is also some property of some materials which are reluctant to give response to the applied magnetic field. And the next one, residual magnetization or residual flux. It is also we discussed just before. Residual magnetization. So these are the basic magnetic properties that we can understand by studying the hysteresis loop. So this is all about the hysteresis process, and if you are understanding with the help of this video, and if you want to ask any questions, you can make it in the comment box and I will reply in my next video. Thank you.